Lucas, this is your first time at Extra Help?
Yes, sir.
Wow. Lucas's first time here at Extra Help. Well, excellent. We should celebrate, huh? Excellent. These are, Rachel doesn't come very often. Rachel, very nice welcome. Welcome to Rachel. Okay, these other guys I see a lot. Gab, Carly, I don't see you a lot. I should see you more often. Okay.
There she is.
There she is. We have a guest here coming in here. Oh my God! Look who's here. Okay, let's ask. You can come in too. Katrina's here. The crazy Latvian. God bless her. God bless all Latvians. Okay. So let's do this problem. This problem will give a nice introduction to chapters 21 and 22. Okay. Now, I'm going to do an experiment. I want to find the specific heat of an unknown metal. Now, let me say a word about specific heat capacity. Specific heat capacity is the amount of heat needed to raise a certain mass of material 1 degree. 1 degree Celsius. Right? The amount of heat needed. For instance, water, if you look at water, it takes 4,180 joules to raise 1 kilogram 1 degree Celsius. Okay? It's a lot of heat. Correct? Yes? All right, you all right with that? Okay. So, I want to know what the specific heat capacity is of this unknown metal, given this data. Now, specific heat capacity is a unique physical characteristic property that can be used to identify a substance. For instance, if I said to you, I have a clear liquid, it's odorless, colorless, it boils at 100 degrees Celsius, it freezes at 0 degrees Celsius, what would you say that was? What substance?
Water.
Water, okay? Because what I said to you was, I gave you specific physical characteristic properties of water. Specific heat capacity is also a specific physical, intensive, characteristic physical property. Just like the boiling point of water is 100 degrees Celsius at 1 atmosphere, it has a specific heat capacity as well. So I can identify the specific heat capacity of the metal. I can use that to help identify the metal. In analytic chemistry, it can be used to identify unknown metals. Simple? Unknown liquids, unknown metals, whatever the case may be. All right. This is the experiment that I'm going to conduct. I'm going to boil a piece of metal. Now, why am I boiling the piece of metal? Why am I doing that? Well, I want a reproducible initial temperature. What's the initial temperature going to be of this metal if I'm boiling it at 100 degrees? 100 degrees Celsius, right? So that's going to be the initial temperature of the metal. Now, I'm going to take this metal and I'm going to put it into 20 degrees Celsius water. You would not want to take a shower with 20 degrees Celsius water, trust me. It's cold water. Even though it doesn't seem that cold, it's cold. But I'm going to take this metal and I'm going to put it into 20 degrees Celsius water. What's going to happen to the water? It's going to increase. The temperature is going to increase. And then I'm saying that it's going to increase to 22 degrees Celsius. Are you with me on that very simple experiment that we're doing? Rebecca, you okay with that? I'm not asking you to solve any problem yet. Brett, just follow along. I take something hot, I put it in, oh my God, we have the visitor. I take something hot, I put it in something cold, and that cold thing becomes, bye, Katrina's leaving. The cold thing becomes warmer, right? Make sense? Okay, now. The initial mass of the metal is 0.2 kilograms, 200 grams. The water is the amount of water I'm going to have is going to be 1 kilogram. Okay? The initial temperature of the metal is 100 degrees Celsius. The initial temperature of the water is 20 degrees Celsius. Why is the final temperature of the metal and the water both 22 degrees Celsius? They're both in the same environment. Correct? Let's say it's 22 degrees in here right now. Okay? What's the temperature of the desk? 22 degrees. What would, if you died, God forbid, what would your temperature fall to? 22 degrees Celsius, whatever the temperature is of the surroundings, right? So if the water is 22 degrees, then the metal is going to be 22 degrees. Does that make sense to you?
Yeah.
Now this is what we can say. This is what we can say. The heat lost by the metal equals the heat gained by the water. Is that okay? Can we say that?
Yes.
Can we say that? The heat lost by the metal is going to equal the heat gained by the water. Is that okay? So this is what we can say, and this is big, 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 big. If I take the heat gained plus the heat lost, it's going to equal 0. Does that make sense to you? The heat lost by the metal plus the heat gained by the water, it's got to be 0, right? One's lost, one's gained, correct? Yes or no?
Yes.
Yes.
Okay, now, I'm going to call this Introduction, no, I'll call it Thermodynamics Part 1, Lecture 1. Is that okay? And then I'm going to come back. We've got to remember this data, we'll remember this equation, and I'm going to solve the problem. Okay? I just simply don't have enough room on the board to solve it as it is. Clear? So that's number 1. Is everybody with me with lecture number 1? That's all I wanted to do. I wanted to describe an experiment to you and show you this very simple equation. That's it. Are you with me? Excellent.